So while you're setting up, I guess my goal is to teach you Python objects from the inside out. So normally in Python, when you're working with objects, when you're working with classes, what you're working with is ideas, concepts that correspond to things within the problem domain that you're trying to solve. So you have an object and it represents a socket, and you think about it in terms of a socket, and it has behavior, it has attributes, information, data, and it has methods for working with it. But conceptually, that object is a socket. And then maybe you have, the example I always use is when we were building a spreadsheet, we had a workbook class that represented the main workbook, and then that had worksheet classes, and the worksheet classes had cell classes and rows and columns. So the object structure there provided structure for the application. We knew if we wanted to modify something on the workbook, the way it opened and loaded files, we knew that the behavior would be in the workbook class. So the objects there, they're ideas. They represent concepts, and they give you ways of thinking about the behavior of the system. You can understand and reason about the system because of the object structure you use. So fundamentally, an object is an idea. And if you actually come right down to it, the computer is executing machine code, binary code, however you want to say it. The computer knows nothing of your objects. The objects exist for developers to think about. And Python interprets your ideas into something that the computer can execute. But the step beyond that is that in order to be able to represent and to model things within our problem domain, we need to understand Python. We need to understand how Python works. We need to understand how to be able to produce behavior. And that's what we're going to look at now, is the internals of Python, what a Python object is, and how it's represented, and how we can control and modify its behavior. So on the PDF, we're jumping in at operator overloading. That's page 93 on my machine, just after exercise 7. You're welcome to keep these materials, obviously. They are the teaching materials I use, so please don't distribute them. They are copyright to me, but you're welcome to keep them and refer to them and read through the rest of the course. I don't know how much sense the rest of the course will make without me jabbering to explain it. But okay, so who's familiar with the magic methods, the double underscore methods, the dunder methods? Yeah? Relatively straightforward. So we'll whiz through this. We probably won't do the exercise on this one because the exercise is very tied to the course. But it's such a fun. In fact, before we get there, let's get up to speed on Python objects. So we say in Python that everything is an object. And the is-a relationship in computer science is via inheritance. So everything inherits from object. So everything is an object. Classes are objects. Everything is an object and everything has a type. So you can ask the type of things. Type X, the type of X is object. We instantiated object, we created a new object. So the very basics of Python objects is everything is an object, everything has a type, and objects are created by instantiating their type. Could you close the door, actually? I mean, more people are welcome, but it's noisy. There's a zip file which belongs to somebody else and we need to keep track of that has the material I'm working through. And when we say everything is an object, that actually means something. That actually has consequences. X is an instance of an object. In the inheritance hierarchy of this class object, object itself remains right at the top. And we actually get some behavior from that. It's not just some nice theory. Attribute lookup. So let's just attach an attribute to the class. We're going to look at attribute lookup a bit more clearly in a bit. But attribute lookup is actually implemented. It actually lives in the get attribute, the dunder. So the Python magic methods, the special methods, the protocol methods, they're all ways of saying the same thing that exist in Python. They start and end with double underscores. That doesn't mean they're private, but what it does indicate is that in general you don't call these directly, not very often, not never, but not very often. But the Python interpreter calls them for you. And we can do operator overloading, we can overload this built-in behavior. And done to get attribute is where all of the object access protocol is implemented. So when I do x.foo, if I look in X, I don't think I'll see. Yeah, I don't see done to get attribute as an attribute on X itself. It is there. Yeah, it comes from. But if I look at x dot done to get attribute, I think the repr is going to tell us something useful. Right. Yes. When I look up the done to get attribute method on my class, the repr tells us this actually comes from object. So what we're seeing is that fundamental behavior of Python objects come in consequence of everything being an object, which in a practical sense is because everything inherits from object and the actual behavior lives in the object class. It's not just an empty placeholder. The other one is that most classes inherit and use is the default repr. So if you call repr on an object and you haven't overloaded done to repr, is this big enough? Can you see it at the back? Shall I bump up the font size?
Just a bit.
Okay. Didn't quite do it. Oh, for goodness sake. When you set the font size above a certain size, the OK button is actually obscured from view. Okay, there we go. That's a bit bigger. So we say everything is an object. Every object has a type. You create objects by instantiating their type. So the interesting question is, if a class is an object, what is its type? What is instantiated to create the class? And that is what a metaclass is. And we're not going to go into it in detail now, but the default metaclass is type. Let's have a look at the type of X is type. A class is an instance of the type. The type is the default metaclass, and you can create new classes by calling type, by instantiating type directly. What they take is a name, which is a string, a tuple of base classes, and a dictionary of class members, which will be functions for methods. And just to show you that this works, so this is a class factory, and it's actually a useful technique from time to time to be able to dynamically build classes. So there I've built a new class X. And I can instantiate that, and I get an instance of my X class. So that is essentially metaclasses. There's a lot more to the machinery and how it works, but that's the basis of metaclasses. Okay. So, back to the, oh, for goodness sake. It's Control L to go full screen, not Windows L. Windows L locks the computer. I despise Windows. Okay. So the Python protocols, the magic methods, they're effectively interfaces, protocols, but unlike many languages, they're soft interfaces. So just as we have duck typing in Python, that you can use an object, so long as an object looks like a duck, quacks like a duck, we'll treat it like a duck. It's the same with these protocols. If you implement the right protocol method, Python will use it. But you only need to implement the ones you want to use. You're not required, except in certain circumstances, to implement the full protocol. And so equality and comparisons are a protocol. The container protocol is my favorite. And the numeric protocol is a lovely example of the horrors contained within. If you want to make an object behave like a number, you can. You just need to implement dunder_add, dunder_sub, dunder_mul, dunder_div, dunder_floor div, mod, L-shift, and then there are right-hand variants and in-place variants of some of those as well.
You can also probably do the same thing as we saw Raymond showing.
With the abstract base classes?
Yeah.
Right. And there are abstract base classes, particularly in the collections module. I don't know that there is a numeric tower of abstract base classes as well. Yeah, and so you should very rarely implement all of these, and particularly for the container protocol. The container protocol, I think, if you inherit from mutable mapping, you only need to implement these three, something like that, and you get all of the others for free. And I think that comes up in one of the exercises. But yeah, the abstract base classes really are very cool, particularly for the protocol methods. So the difference between dunder_repr and dunder_str. Would anyone like me to explain that difference?
One for printing, one for converting to...
Yeah, a representation for humans and a representation for geeks. The very basics of the container protocol for fetching items by index or by name. There's no difference at the Python level between the sequence protocol for fetching items and the mapping protocol for fetching items. Dunder_get_item. Dunder_set_item for setting items. The thing that is really neat about containers is when you're implementing these protocol methods, what you're doing is you're giving your object a particular API, a particular interface. It's like even with the numeric tower, it's not just numbers that have dunder_add, strings have dunder_add, pathlib, the path objects in pathlib, you can add paths together. And what you're doing is you're saying, my object supports the addition operation. Addition is meaningful for this object. Now, there's no reason why you would need to use the plus operator unless you really are implementing a method. You could just, a number. You could just have a method that says, add another one of these and return me a new object. But if you have objects that it feels like you ought to be able to combine them together, then by supporting the addition operation, the plus, you're giving a nice API to your object. If your object conceptually stores mappings of, say, names to some other object, The example that I work through in this course is we have a location. I build up a location object. It's for the Ordnance Survey who work on maps. So we have a location store mapped by the town name, mapping to the location object. And this store can do various things like fetch data from the internet, populate itself. And we start off with a get location method. But actually it feels like a mapping. It feels like there's a correspondence of name to object. So if we give it the container, if we implement the container protocol, we give it an interface, an API, that people already know how to use. You can say, this is a mapping, and people will expect certain behavior, and that behavior will then be intuitive. So the purpose of a lot of the protocols is part of your, it's part of the way you think about the object and how the object is going to be used. It's part of API design, making an object that is easy and pleasant for your users. So we won't do exercise 8. Let's take a little step back and understand assignment in Python. There are lots of ways of doing assignment. This is a straight assignment. This is assigning into, say, a sequence. This doesn't create a name. This creates a name. Here we're appending to a list. Unlike other languages, assignments don't create copies. The object is not copied. We create a reference to it, and that's fundamental to Python. Everything is a reference. And this is particularly important when you're working with mutable objects. Here we have a list A. Then we do B equals A, and then we do C equals A comma B. How many list objects are there in that in this bit of code?
3. No, 2.
Yeah. We create a list object. We create another reference pointing to the same list object, and then we create a new list. So this is the second list. And in the first slot in the list, it's got a reference to the original list. And in the second slot, it's got another pointer to the original list.
You can even, I think you can even point append list to itself.
Yep, yep.
It will be printed as
So you can make recursive, so you can use lists to build up and dictionaries to build recursive data structures, graphs with pointers back into themselves, yeah. You can do, here you could do A.append A or C.append C. It's just a pointer. That's what a reference is. And the trouble with that is that if we then mutate one of the lists via any of the references we have, that difference shows up everywhere. So be careful when working with mutable objects. And the same with, so when you pass a mutable object into a function, it's often very important to know, is that function going to perform any destructive operations? I know in JavaScript date objects are mutable, and there was a calendar widget that would modify the date object you passed in. So you would pass in a date object and display it, and it would be you would have other references stored to it, and they would all be changed. It was very surprising behavior. So this, whether objects are mutable or immutable, obviously most of the containers, the collections are mutable, and it's important to know, if you hand off the object to some other code, what is that code going to do with my object? And here we'll look a little bit at name binding. A, we create a list containing 1, 2, and 3. B, we create a new reference, a new name, bound to the same object. If I then do A equals 4, 5, 6, how many references are there to this list here after we've executed this line of code? Yeah, because this takes this name, which was pointing over here, and it rebinds it to point to a new object. But we've still got a reference, B, pointing to the original list. If we then did B equals A again, there would be no more references to this. Python uses reference counting for garbage collection. The reference count on the list would drop to 0, and it would be freed. So we have this important distinction between identity and equality. So here I've created, I'll tell you what I'll do.
Sorry, I have a question.
Yeah.
But when it will be cleared from memory?
Okay, so that's there are all sorts of disadvantages to reference counting. The advantage of reference counting is deterministic garbage collection. Inside CPython, the decref operation is a macro. So you'll see in the source code this decref, decrement ref, all over the source code to reduce the reference count. And that includes checking if the reference count has now reached 0, the object is immediately freed. The only time that's not true is when you have object cycles. This, if we did, so let me create a new, we created a list, C. If I do C dot append C, now let me, is it weakref dot ref? Okay. So I'm going to take a weak reference to our list. A weak reference is a reference that doesn't keep the object alive, and it's useful. You can use it to avoid creating object cycles, or if you want to keep track of something but you don't want to prevent it being garbage collected. At some future point, you might want to say, if you're still alive, I want to use you and inspect you, but if you've gone away, that's fine. So here, can you not create a weak reference to a list? Good God, man. Right, let's try this. I don't use weak references very often. All right, so where are we? We're up to D. Let's do D. Let's instantiate A. Let's create a weak reference to our instance. Woo! Okay, so now object D, I'm going to so D is an object. I've attached a reference to itself onto the object. You can see that? So the object D is an instance of A. The class A is just an empty class. It has nothing else. But I've given the object D a reference back to itself. And if I now do sys.getRefCount on the D object, it's probably going to say 3 or 4. 3. Right. Sys.getRefCount will tell you how many references there are to an object. It always inflates the answer by 1 because getRefCount has a reference to the object. And there are 2. One reference is D, and the other reference is D.D. If I do, so I have our weak reference E. If I call the weak reference, it returns the object. That's how you get the object back. If the object has gone away, it returns none. So let me do del D. Okay, now normally, at this point, the reference count would have dropped to 0. The object would have been collected, but I think because the object has a reference to itself, the reference count never drops to 0. So there is also a cyclic garbage collector in Python that kicks in periodically. It has to stop the world, and it finds object cycles and then collects them. So in general, the answer is, when does an object get collected? The answer is, in general, as soon as the reference count drops to 0. In the case of cycles, you have to wait for the cyclic garbage collector.
Okay, one more question. Does it have like 3 buckets?
The memory allocation strategy?
No. I'm sorry. My English is not very good. Да. Есть в нем как бы 3 корзинки для совсем старых объектов, для тех, которых моложе, и вот совсем молоденьких, и они перемещаются.
Yeah, so the question is like, does it have different generations of object to...
It's not a generational collector, no. Because it uses reference count for the main collector, and for the cyclic garbage collector is looking for cycles where there are no external reference to the cycle. So it doesn't do. It's not a generational collector. It doesn't need to be.
I actually believe I also saw that on some talk. Like maybe it's not about generations. Maybe it's about like the frequency where it's collected or something. Because like if the object exists,
Oh, I see.
it's supposed to exist for a long time, then collector looks at that object.
Well, that's what a generational collector does. I don't know if Python does any of that.
I think it does.
Maybe.
But,
Yeah, that's normally true of moving collectors, generational collectors, though it's not normally true. It may be. Anyway, I wonder if D has gone away yet. I wonder where the references are. There's a reference somewhere which is. Ooh. Anyway, let's get back to the difference between equality and identity, which is an important distinction in Python, because everything is a reference. The name A is a reference, points to a list object. The name B is a reference pointing to or bound to another list object. And for list objects, equality is defined as if they have the same contents, if all of the members, if you compare two lists, the members will be compared, and if they're all equal, then the two lists are equal. So A and B are equal. A equals B, but A is not B. They're different list objects. Even though they're equal, they're not the same object. And that's obviously the case, because as soon as I append to A, obviously B is unchanged, and A is no longer equal to B. So there's this very important distinction between identity and equality. For some things, like none is a singleton in Python, there's only one of them, so you can always check for none with the is operator, the identity operator. The same for true and false. They're singletons. You can always check for them with is and is not. And that's faster. And some of the style guides, like Flake 8, if they see you doing equal none, will tell you should be using is there, because it's more idiomatic Python to use is or to check identity, and it's much faster because it's just a pointer comparison. Okay. One of the ways Python does this is every object has an ID. The ID corresponds to its memory location. And in terms of blowing people's minds, so A, we can ask for the ID of A. That will be a unique number representing A. And sometimes it's useful to, instead of using weak references, you can keep track of objects by ID. So we know that this is not true. Empty list is not the empty list. Does anyone know why that happens?
Some cache mechanism.
Sort of.
Each
Sorry?
empty list is instantaneously garbage collected.
Yep. There's one reference to this list object. It's created, it's passed to the ID function. When the ID function returns a number. When the ID function completes, the reference count to the list drops to 0. It is immediately collected. We then come to executing this code. A new list is created. It is given the ID from the object that has just been created and destroyed. And it's a quirk of the implementation of CPython that this happens to always be true. It's never useful in code. It's never a useful fact to know. It's only useful for showing off to other Python programmers. So even if you get nothing else out of it, you'll be able to impress people with that one. Okay. So just quickly reinforcing the point about mutable lists and shallow copying. If you have a list and you're going to pass it around to somewhere else, and that somewhere else might perform a destructive operation, maybe you want to take a copy of it. And this is how we copy a list in Python. Most of the other types will let you, the dict will let you do something similar.
Again, the same as typing a slice of alt, right?
Yes, yeah. Yeah, there are various ways of doing it. Yeah, taking a slice always creates a new list. So if you slice with just the colon in it, you get the whole list. That's an idiomatic way to create a copy of a list as well.
There is also built-in module called copy.
Right, and we'll get to that in the very next slide. Because the problem with this is this creates a shallow copy. What this says to Python is create a new list, and the object that is pointed to by slot 1, put a pointer in slot 1 to the same object, a pointer in slot 2 to the same object, because it's all pointer copies, everything's around. The object in slot 3, let's have a pointer to that in slot 3 of our new object, and that is a mutable object. And we've now got two references to the same mutable object. So if we pass B, our new list, which is not the same as A, it's a new list. If we pass that to a function and it mutates the inner list, A and B will both still see the change. Do you get that? Because it's a mutable object containing a mutable object, and a shallow copy just gives us a top-level copy, and we've still got in A and B this same pointer to the mutable object here. And if you want to work around that, you need a deep copy. And as you say, this comes from the copy module. Deep copying is very complex because it attempts to work around as much of the Python object model as possible. For simple data structures like lists and dictionaries, it's pretty efficient. It has limitations. You can't copy a socket. You can't copy a file handle because the internal state is owned by the operating system. The internal state is opaque to Python. So if you have a data structure or an object graph that you want to copy, and it has something like a file handle or a socket in it, deep copying will fail. And pickling will also fail in the same way. You have the same limitations with the pickle module that you have with the copy module.
This also leads to that also like party trick with Python where you can actually modify a list inside the mutable tuple.
Yes.
With plus equals, which unrolls to extend an assignment. So extend works, but assignment doesn't. So you get both things. You get
Yes, the mutate happens, but the assignment fails. Yeah. Okay, so everything is an object. All objects are first class. So there are no special kinds of objects in Python. And here's a lovely trick that, again, you're possibly familiar with. This is as close as Python has to a case statement, case and switch. And here we're checking if the operation is a plus, perform the add operation, call the add function. If it's a minus, call the sub function. If it's a star, you can imagine this might be a calculator program or something like this. We can actually put the function objects into a dictionary keyed by the operator. And then you can look up the operation to perform rather than going through this if-elif. It just becomes a dictionary lookup on the operator, which returns the appropriate function object and calls it with x and y. And so once you've done that, this code looks much nicer than that code. And it's a consequence of functions are first-class objects. We can store them in data structures, and that's the basis of functional programming in Python. Higher order functions, functions that return functions, or functions that take functions as arguments. Right, and there's a really silly little exercise, so you can use your computer, exercise 9. It's really just some code for you to type out. So if you go into the code folder from the zip file, no, go into the exercise folder, exercises, and it's exercise 9, which is an HTML file. And why have you opened all the... So this is code to type at the interactive interpreter, and we're just demonstrating that everything... So if you see in any of the exercises code that looks like it's been typed at the interactive interpreter, that means it's code for you to type and follow along with. And just look at and make sure you understand what is happening. So it's a nice simple exercise to get you warmed up. What time are we carrying on till? Is it 10 past 5, is that right?
They just said that you have a talk and I didn't give any minutes. That's 10 minutes. So just keep going.
It's only 3:30 now. I think 10 past 5 is when I was told, because I think there's probably the closes. So that's 40 minutes. So we've got a good amount of time still left. There's more to come. It will be much easier to read if you open it from your computer. Do you have the zip file?
No.
Ah. You don't have a USB stick? A USB?
Oh, thank you very much.
You cool kids with your modern thin computers. I'm going to go and vape for 2 minutes.
You know, the whole story on that one is a big difference, so everybody has perspective. Be back in less than 2 minutes. Я сам долго искал, забыл, что у меня есть.
Даже не брал.
iTunes спрятать и сказать, как этот код работает. iTunes это секретный список. Флешку у кого? Скажите. Liskov вообще все красиво.
Нужно просто фронтенд засунуть модуль, чтобы он глобал спрашивал, когда он туда лекцию.
Did you all get through that okay? Anyone got any questions about stuff we've done so far? You all want me to get on with it? Okay, so we're going to get to the fun parts of the object model in a few minutes. Let's look at inheritance. What is inheritance for? Why do we use inheritance? I think the most practical reason for inheritance is a mechanism for code reuse. This is the syntax. If you're using Python 3, you don't need to explicitly inherit from objects anymore. The parent classes are expressed comma separated if there are many of them when you declare the child. So we call this the parent class, the superclass, the base class, and this is the child class, the subclass, the derived class. That's straightforward. I'm sure you've seen that before. And we can specialize existing classes, we can add new methods, we can override new methods to change behavior, and we can add new attributes. So it's all about taking existing code and extending it in some way. Here's a very simple example. Through the course there, we've had a stock class which has a cell method. It has this is the name of the symbol, this is the number of shares, and this is the price of the shares in a floating point number. You should never use floating point numbers for financial operations because they are an inexact representation. However, guess what the most commonly used tool for tracking financial data is Excel, and guess what it uses as its basic number type. Anyway, Okay, so shares have a sell method. Here we have a holding of 100 shares of Google. We've sold 25, we have 75 left. The price crashes, we panic, and it sells all of them. We've extended the stock class and added new behavior to it. Here we're trying to con our investors. So we're trying to inflate the value of all of our holdings. So we're overriding the cost method. And we're inflating the value. The cost is the number of shares by the price, and we're multiplying it by a factor of 25%. So the interesting thing to note is that here we're defining a new method, panic. We're calling the sell method, self.sell. So Python on a myStock instance, when we call panic, this is a myStock instance, it looks and it finds the panic method on myStock. The panic method calls the sell method. Obviously, you can see the sell method doesn't exist on myStock. So Python finds it from the base class, from the parent class. And how it does that search, how it finds that method, is the full attribute access protocol. And as soon as you have multiple inheritance, it gets really tricky. But it's actually possible to understand, and that's the Python method resolution order, and I'm hoping we'll have time to get to that. Because multiple inheritance, although you should do it as little as possible, is very useful and is widely used for mixing classes. And that's perfectly acceptable use of multiple inheritance. And how methods are looked up is it's complex, but the rules and the mechanisms are very possible to understand them. So if you've not looked at the method resolution order before and not really looked into multiple inheritance, it's a really interesting topic. Okay, here we're overriding cost. So even though there's a cost method on the stock class, when you create a myStock instance, when you call the cost method, the one on our class, the overridden method, is found first and used. Again, I'm pretty sure that will be straightforward to most of you, pretty basic. Here's where we start to get to some knowledge that might actually be useful. We're looking at our stock object. We're creating our myStock, which inflates the value of our holding. And maybe the cost is a little bit more complex than just shares times prices. We don't know. We don't know how the cost is worked out. So what we want to do is we want to use the base class implementation, and then we want to modify it. So in this, instead of repeating in the last implementation, we just completely replaced cost. We had a new implementation of cost. In this version, we want to call up to our superclass, to our base class, and we want to use that method. Now, this is where there's a very straightforward rule. Always use super to call up to a parent class. I'm going to explain why in a bit, but if you've ever done anything else, if you've ever written anything like stock.cost_self, stop doing that and use super. And in Python 3, we made it super easy. So super, called like this, who used super in Python 2? Who's used to the Python 2? Sort of, yeah.
It's actually trickier in Python 2 because there is such thing as class object, which is like a part of all style classes.
Yes, yeah.
All style classes, super doesn't work.
Yeah, you must. So the first rule of Python 2 is don't use old style classes. In Python 2, the syntax was something like this, and it's something like, it's type an object. So you would do something like myStock, self.cost. This is what you would do in Python 2. Because of the way the method resolution order works, because of the way that the base class implementation is found, super needs to know what's the class of the object I'm in, and what is self, what's the current instance. But nobody could ever remember which way round those two things went. And it was a real pain, that was myself included. And so in Python 3, you can write this. Now, it's really interesting because it's an example of one of the things that happens at compile time in Python. Python is bytecode compiled. So the first thing that happens before code is executed is it's compiled into bytecode. We still say it's an interpreted language. I mean, Java and C# are both have an intermediate language. They're both bytecode compiled as well. Java has a just-in-time compiler, Hotspot, widely considered to be the world-class just-in-time compiler. .NET uses an ahead-of-time compiler. The speeds are about comparable, and the .NET guys say that's because their garbage collector is world-class and outperforms the Java one. So the performance is about a wash usually. But the hotspot JIT is good. So we tend to call Java and C# compiled languages, even though they're bytecode compiled, and we tend to call Python an interpreted language, even though it's bytecode compiled. And what happens is at compilation time, the Python sees you're calling super, and it fills in self and mystock. It knows what self is called from the AST or the concrete syntax tree actually, and it knows what class is called as well. So it just fills in those two for you, and that happens at compile time. So it's a bit of magic. But it's really easy. And what's happening here is inside when cost is called, we say call the base class version. So it calls this, it returns the value, and then we modify the value and we return the result. So hopefully you can see what's happening there, relatively straightforward. And of course with inheritance, a place you're pretty much always going to want to make a supercall is if you override the initializer. Who knows why this is an initializer and not a constructor?
Because there is also a dunder new method.
Yes. Dunder init takes self as the first argument. Self is the instance. So when dunder init is called, the instance has already been created. So languages like Java that have constructors, they're not actually constructors because this already exists inside the constructor. They're initializers. Those languages conflate initialization and construction, and Python does not fall into that trap. We are not so gauche. Python has two-phase object construction. And dunder new is the constructor. And it takes the class as the first argument. So it's kind of a class method, I guess. It's not actually a class method, but... Now, an interesting thing that dunder new is free to return whatever you want. So this is a really interesting class. When I instantiate foo, it always returns 3. That's perfectly valid Python. Okay. So the rule for dunder new is if, so long as dunder new returns an instance of the class or a subclass of the class, then the initializer will be called. And we delegate to the actual work of constructing the object to object.dundernew. And this in particular is why you cannot create a true singleton in Python. There are lots of tricks to create things that look and feel like singletons, but as soon as someone's got hold of your object, they can always find the type, and there's no way from within pure Python code of preventing them doing asking object, create me a new instance of this type. So trying to create singletons in Python is a fool's errand, and the simple rule goes, if you only want one instance of an object, only create one instance of the object.
We can sometimes just use module as an object, because module by itself it behaves like a singleton.
Right. Yeah. Okay. So the rule is, so long as dunder new returns an instance of the class being constructed or a subclass, then the initializer will be called. So now when I instantiate foo, the constructor is called, a new subclass is created, and an instance of that subclass is what's returned. So here, the type of f is not the same as the type of G. Every instance has a different, but you can see that the initializer has been called in both cases. So it's an interesting thing to be able to do. The main point here is the point about dunder_new being the constructor. There is actually, I did actually find a use case for this in mock objects, if you've ever used the mock library. One of the things about the special methods, the Python protocol methods, like dunder_getItem, dunder_setItem, dunder_repr, is there's a fast path in the interpreter, and they're not, the full attribute lookup rules don't apply. They're not looked up on the instance first. The magic methods are always looked up on the type, on the class. And I wanted magic mock objects to be able to behave like containers, so to be able to have a dunder_getItem that you could customize. The trouble was that if you customized dunder_getItem on the class of a mock object, if they were all instances of the same class, then as soon as you modified the class, that would affect all mock objects. It would change the behavior of all mock objects, all instances of that class. So the code doesn't quite look like this. I think I used the trick of type to create a new subclass. But every mock object, every magic mock instance is actually an instance of a subclass of magic mock created in dunder_new, and then you're free to attach whatever method you want to the class of a mock object, and it doesn't affect any of the other mock objects. So I did find a practical use case for this corner of the Python object model. So that's Python two-phase object construction. This is initializing your parents. It's quite a common mistake to override dunder_init, forget to call up to the parent class, and then our stock objects, look, the initializer takes these arguments. If we forget to this line of code, then when you instantiate my stock, these attributes won't have been set. We'll have a partially initialized object. We'll have a broken object. And again, when you call up to the base class, always use super. And I said a little while back that the most practical purpose for inheritance is code reuse, specializing existing code. The object-oriented purists would say that inheritance creates an is-a relationship. So a myStock instance is a stock by virtue of the inheritance relationship, by virtue of the child-parent relationship. And so you can use inheritance to create a hierarchy, a taxonomy of objects. That's actually useful. That's actually used in Python for exceptions. Exceptions are one place in Python where effectively they're type checked. When you do exception handling, you put the type of the exception you're expecting, and Python matches the exception type against those, against the types in your except clauses. So it's very common to have to create an exception type by subclassing an exception. You might have a very general exception for your library, my exception, and then you might have a hierarchy of different types of exceptions, and that allows people either to catch a very specific exception, or if they just want to catch any exception your library might catch, to catch the more general exception at the top of the inheritance hierarchy. And there we really are just using inheritance to create this taxonomy of objects, to create this relationship, rather than particularly for code reuse. Does that make sense?
In Python 2 it was also somewhat broken because some of the internal exceptions, like on the deep level, they weren't inherited from exception class. Something like, I believe, socket error and some stuff like that. They fixed it really soon, but for some time there were several exceptions that would actually happen and you wouldn't catch them even if you followed just
Okay, I didn't know about that. So,
that exception.
but I wonder which version of Python that was.
2.5, I think. But,
I'm skeptical.
Like 7 years ago or 8 years ago.
You used to be able to catch strings as exceptions. You used to be able to raise string exceptions. And that was a nightmare. So they deprecated them and they only got rid of them about Python 2.5. I wasn't aware of any uncatchable exceptions. You might be right. I'm just skeptical.
It's also always tricky with exceptions in C libraries. Because
Right.
another level of pain.
Yeah, and that's not something I've had to work with. So yeah. I'm interested. I'll look that up later. Who knows the Liskov substitution principle? No, I won't make you explain it. So the basic principle, the Liskov substitution principle, first propounded by Barbara Liskov in 1987, is that when you subclass, when you create a child class, you should leave the same interface. The subclass should have the same interface as the parent. You're allowed to add methods, you're allowed to override methods, but where you override methods, you need a compatible signature. And this is the basis of polymorphism, and this means the basic principle is anywhere in your code that works with parent also ought to work with child. And this allows, that's the basis essentially of the type system in most statically typed languages, that you can pass in, you can declare the type, you declare the type of a parameter, but it will actually take any type derived from that as well. It's useful in Python, but we have duck typing, which is more flexible than polymorphism anyway. You can achieve the same thing without actually even having to inherit. But this is considered one of the principles of computer science. And again, as with all rules, the real trick is knowing when to break it. Somewhere else in Python that we use the is-a relationship. When you're writing tests in unit test, you inherit from test case, and the unit test test collector will look for all classes that subclass test case. It uses that identity, that is a relationship, to identify your test classes. Right. So it gets more interesting when we add multiple inheritance into the mix. This is a fairly straightforward hierarchy. We have a class A and we have a class C. B inherits from A, and D inherits from both B and C. So the type of multiple inheritance that Python has is called cooperative multiple inheritance. And there are other types, and other languages only have single inheritance but allow interface declarations, so you can sort of get multiple inheritance. But the idea is that the child class here can customize its behavior not just by inheriting from the parents, but by the order it puts them in. And these parents need to cooperate with each other. So when we look up an attribute on the child, the attribute may be found on any one of these parents. And the basis of that cooperation is super, which is why you should always use it. Because, yes, we'll get there. I'll do this as an example to show you because it's interesting. So we have class A. I have to remember it and type it all right. So now we have class B that inherits from A. Now we have C that inherits from A
Why don't you use IPython? Just wondering.
IPython. Because particularly when I'm teaching less advanced courses like Introduction to Python, idle is more than good enough. It has some features that actually make it particularly suited to teaching, and it's really useful if everyone has the same thing. So I'm just used to opening idle and rattling out examples. Less complexity can be better. It's really useful to be able to write a bit of code in an editor, execute it, have it execute it here into the interactive interpreter and drop me into the namespace of the code that's just executed, because I can bang out a bit of code, hit F5 and start using the code. And there are very few things that allow that just as fluidly as idle does. Okay, so we have class A, which is our parent class. We have B and C that both inherit from A. We're going to create class D. And I think it goes BC. Okay. So I'm going to instantiate D. I'm going to call D.spam. You've all got the exercise, the slides, haven't you? So there's no point in asking you what happens. You'll just look at the slides. But let's see what happens. So our class inherits from B and C. Let's look at the code for B. So when we call spam, Python has to obviously look up the span method. The B child class is declared, sorry, the B parent class is declared first. So it's fairly natural, easy to understand that that's would be checked first. So B is printed. Let's look at the code in the B class. It's a very simple class. It inherits from A. When we call spam, it prints B, and then it makes a super class call to its parent class. So if you look at this code, what would you expect this line of, where would you expect this line of code to go? You would expect it to go up to A, wouldn't you? But what is actually happening is first B is printed, then C is printed, and then parent is printed. And this is why you should always use super, even if you're not using multiple inheritance. Because we're using multiple inheritance, self here at this point is an instance of D. When this code is executed, super.spam, it jumps here to C. And then C is called, and then A is called.
But why? It jumps to the next inheritance and multiple inheritance.
Right. I will explain. So the thing is, if it went from, first of all, let's see why it couldn't, why multiple inheritance couldn't work if it went BA. So it goes to B, B calls super, it goes to A does not call super. So C would never be called. C would never be used. And don't forget, this is in cooperative multiple inheritance. The parent classes can cooperate with each other. If you had a mixin class, and your mixin class wants to add extra behavior, what you don't want is the supercall just to walk up the mixin class, which you've put first, and then stop. It wants to customize, the mixin class wants to customize the behavior. So, but let's look in a little bit more detail and understand this. But the interesting thing to note, it's gone sideways. The supercall went sideways. It didn't go up. Okay, so cooperative inheritance is the basis of being able to use classes via inheritance as composable bits of code. And that's the basis of mixins. So before I explain the mechanism, let's show a practical use case of it. Let's show why it's useful. So here we have two classes. We have the dog and the bike. They both make a noise, but they're utterly unrelated classes. They're not in the same inheritance hierarchy. They're doing different things. And we want a loud, but they both make a noise, and we want a loud version of both. So we inherit, noise is overridden, the parent class is called, and then we uppercase it. So the loud dog will say woof in all capital letters. We have our bike, which makes a noise, and when you call noise, it says on your left. So we have a loud bike version, which subclass is bike. We override noise, and the superclass noise now calls up to the base class implementation, and then calls .upper on it. And look, we've got exact code duplication here. But these classes are not in any way involved in the same inheritance hierarchy, so we can't just sort of... How can we get rid of this, this code duplication? One of the ways is via mixing classes. And a mixing class, the purpose of the class is to mix in extra functionality to another class. And they're very common. They're very common indeed. Here's a real-world example from Flask. If you're using the Flask Login extension to provide login functionality for your web application, the Flask Login, it needs your user model. So you're inheriting from db.model. This is SQL. This is the object relational mapper. This is SQL Alchemy we're using. We're declaring the user model. We have an ID, which is the primary key. We have a username, string, an email, and a password. And the thing is, most user models in web applications have at least this stuff. And if your user model is fairly standard, what Flask Login needs in order to work is it needs like 3 methods on your user object. And so you need to implement these 3 methods. Except if your model looks a bit like this, they're going to be the same. Those 3 methods are going to be the same for every web application you write. So Flask provides them ready implemented as a mixin that you can just drop in as a mixin class. Mixins go first so that you can customize the behavior of the other classes. You need them to come first in the lookup order. So mixin class is always to the left. So here this user mixin adds in a few methods to user that is going to be used by the Flask Login extension. Mixin classes are actually pretty common. So let's look at what we do. At how we've got this code duplication with our noisy dog and our noisy bike. We can create a loud mixin class. Inherits from object. It's not related in the inheritance hierarchy to the other 2 classes. It has a noise method. And what that does is it makes a supercall to its parent class, to the parent implementation of noise, and uppercases it. Where's the parent implementation of noise? This class is not usable on its own. It's not very testable on its own either, which is another matter, which is another issue. But if we mix it in to our dog or our bike class, and the supercall, what the supercall does actually is it goes to the next class in the method resolution order. And because we're using multiple inheritance, and because the next class has a noise method, this supercall goes sideways. So we can use this class, we can mix this loud class into any class that has a noise method returning a string, and we'll get a loud version of it. So that's how why you might want to use it and how you would use it. That doesn't really explain how it works. The key thing, the key trick here is super doesn't go to the parent class. It goes to the next class in the method resolution order. In the case of single inheritance, the next class in the method resolution order will always be the parent class. which is why it's tempting to hard code the parent class here. But if something else subclasses loud and uses multiple inheritance, even though this code is only using single inheritance, if something using the code uses multiple inheritance, suddenly super needs to go sideways. And this is why you always use super, even if you have no intention of using multiple inheritance. Because if someone down the line is inheriting from your code and they happen to want to use a mixin class, if you haven't used super, if you've hard-coded the class name, 5 minutes, then your code might be broken. Right, so I might not get to explain the method resolution order. What I can do is explain inside Python objects. Dictionaries are namespaces, or namespaces are dictionaries, names mapping to objects. This wasn't very practical in the end, this course, was it? It was more of a long lecture, I'm sorry. And so a module is a dictionary, a mapping of names to objects. Instances, the attributes of an object, are names mapping to objects. And it won't surprise you to know, in fact, you may already know, that instances have a dictionary that stores those names mapping to objects. So we instantiated our class with the symbol, the number of shares, and the price. And there is actually a actual dictionary attached to the object holding the name, shares, the number of price. And operations on the attribute of the instance correspond to operations inside that dictionary. And you can try that, and there's the exercise that comes after this takes you through playing with that a bit.
No, I actually think it's a little bit more tricky because it's...
This is a simplified version of the attribute access protocol. The full attribute access protocol is implemented in object.dunder_get attribute. And yes, if you add, it's more complicated than that to everything.
It's just dunder_dict is kind of not actually a dictionary, like not an actual dictionary.
For an instance it is, for a class it isn't.
Okay.
I mean, I'll prove it.
Just like,
So
yes, it's kind of like an object that...
b.a equals 3. Let's create a dictionary. Now let's do b.dunderdict equals x. b.dunderdict is x is true. It really is a fucking dictionary. And there's b.b. For classes, it's a proxy dictionary.
I remember there is also a pattern called munch, where you inherit class from dictionary, and then you also write a crazy line, self_dunderdict equals self, and then you can...
Yeah. So if we think about attribute lookup, so every instance has a separate dictionary, unless you're using dunder slots. I'm not going to go into that. Every instance have a separate dictionary holding the attributes, and this is how these two different stocks, they inherit the same behavior from the class, but their actual instance data, their actual attributes are different because they have a separate dictionary holding the data. However, when we call the cost method, or any method, that doesn't live in the instance dictionary. That lives on the class. And so the class has a dictionary where methods and class level attributes live. And in Python 2, methods used to be unbound function objects. In Python 3, the unbound function object went away, and methods are just plain function objects. So you can pull methods out of this dictionary, you can put methods into this dictionary, you can put functions into this dictionary to add new methods, you can attach functions directly to a class. And so the basis of the attribute lookup rules is first Python looks in the instance dictionary, and again it's more complicated than this because there are things like dunder_get to override it, there's the descriptor protocol to override it. First look in the instance dictionary. Every object has a dunder class attribute pointing back to the class object, so if an attribute isn't found in the instance dictionary, Python can look in the class dictionary. So this is a little diagram of where the attributes live. Of course, it's more complicated than that, because what about inheritance? What about multiple inheritance? And there you have the method resolution order. And the method resolution order, obviously, if a method is implemented on one of the base classes, Python has to find it in the dictionary of that object. And we don't have time to go into the details. You're welcome to look in the materials I gave you. But at class creation, Python linearizes this. So the multiple inheritance is a graph. It's a graph of all the classes. Python needs a linear order to check. So there's at class creation time, something called the C3 linearization algorithm is used. That was what was new in the new style classes in Python 2.2, because there was no super before. You had to hard code the class names, which gave you the diamond problem. You could end up having to initialize parents twice. So the C3 linearization algorithm is used to linearize the inheritance hierarchy. And what it does is it linearizes that following two rules. That the order classes are declared must be honored. So if we have mix-in and then parent, mix-in should be checked before parent. And children should always be checked before parents. So if you have two classes that both inherit from the same class, and this is why we saw it go sideways, then both the children need to be checked before the parent. Because otherwise, a child couldn't override the parent and couldn't customize the behavior. So the rules that Python follows to create this method resolution order, the two rules are the order that they're declared must be honored and children must be checked before parents. And this is why super needs to know the class and the instance object, because suppose this is the method resolution order and super is called, and we're currently, so self is an instance of B. But we're in some code in class A. What the super does is it will go self.dunderclass.mro, gives it the full method resolution order for self, for that object, and it will get this. And then it will say, but I'm in class A. And in the method resolution order of the instance, A appears here. That means the next one is that one. So if you're given self and the current, so if we have, we're due to finish now. Here, look, we have code here, C, and if that's been called from D, self will be an instance of D, right? Yeah. Okay. So this super call can go d.dunderclass, so it can go self.dunderclass, which will actually be B, or whatever it is. It will actually be D. It can get the full MRO for D. It can say, I'm currently in C. I've got the full MRO for D. Find C in the MRO, and now I know which is the next one. And the next one might be a sideways jump. If you play with the examples in the slides and in the exercises, it's not terribly complicated. The thing to take away is always make supercalls, use cooperative multiple inheritance. Multiple inheritance is terrible, except for mix-ins, which are great. Okay, thank you very much.
Thank you.